at the same time. So this is the V over 2 right skin. And this is what I said you have to do in two phases. For example, if you want to write 0, 0, 1, 1, 0, 1, 0, 1 to this row, then you need to write 1 first. That means those cells first. By applying this kind of pattern on this voltage bias, you apply you can do this right in parallel. You can apply right voltage along this row, and then ground multiple columns where you want to write. Okay, set. And then you do the zeros. So you just then apply voltage to those columns, red columns, and then ground this row. So you will write 0. So this is a sequence of the right. And there's another scheme called V over 3 scheme. And this is sometimes used. So the idea here is that still this is a selected cell, and we want to write it. So you want to apply the full right voltage on that. So let's say you apply V here, and then ground here. So this cell will see the full right voltage. And then for the, let's say for the unselected columns, those yellow lamps, we'll apply like 2/3 V here for the yellow vertical lamps. And then for the unselected rows, those are the blue horizontal lamps. So we apply 1/3 V there. And if you check the voltage difference for all other cells, for example, this cell, so what is the voltage difference?
1/3.
1/3, okay. And then how about this cell?
1/3.
1/3, okay. How about this cell?
1/3.
1/3, okay. You will notice that all the rest, okay, cells have 1/3 voltage across. So similarly, you can undo the reset just by reversing the bias like this. I will not repeat here. So, but I want you to compare this one with the V over 2 scheme. So which one is better? Any idea?
This one.
So
Probably more power, but
yeah, depends, right? So there are some trade-offs. So this one, the advantage, let's say V over 3. The advantage is that unselected cell, at most, say 1 over 3 voltage. That means it will have less chance to be disturbed, because the other V over 2 scheme, some cells say V over 2, right? So it's larger voltage, so you may some accidentally write the data, or at least change the state a little bit. So this one is, let's say, more safe. But this one, you may have more leakage, okay? Because all the cells will have voltage difference. All the cells will have 1 over 3 V across that, so that will contribute to the current. So the other V over 2 scheme here, we see that only along this row or along this column, you will have this half select cell. The other cells, like those black ones here, they don't have voltage difference in between the row and column, so they don't leak. Okay. So then you may have this kind of trade-off. So I think you may want to review this in more details after class, because you will have homework on this kind of problem.
How do we generate these many like supplies on the device? Is there
Oh, it's just a standard circuit technique, right? Generate a few bias is not a big deal, right? You just have the bias reference generation, you know. It's standard. Of course, if you want to generate 1/3 and 2/3, of course, it's more overhead than just to generate 1/2. Yeah. But it's doable. So this is right. and then read from the crossbar array. So you have two kinds of read mechanism, but no matter what, you can read in a row in parallel in principle. So for example, you can apply a read voltage here to the selected row, and then ground all the columns. So then you will have current through those cells. And then you want to ground the other unselected rows. And then also here, the sense sample, this node needs to be somehow virtual ground. Then you will read the current from this cell, and then you will determine 0 or 1 by your sense sample. This is more like current mode sense sample. Current mode. The other way is to pre-charge the bitline, okay, by some read voltage, and then the current will flow, and then you ground the selected row, then current will flow this way, and then here for the other unselected rows, you may want to bias to be VR, so they don't contribute too much current to the bitline. They don't contribute here. So the bitline will decay depending on the resistance of the cell. It may decay fast, decay slow. Then you can use the voltage mode sense sample to sense. So we'll talk about the sense sample design later after we are done with those memory cells. So that's the read operation. Any questions? Okay, so then let's talk about why we need the selector here.
In the previous slide, is your bitline also turned on to select a particular cell?
The selector will be turned on when you read. Yes.
The other cells where the word line is off.
Yes. So those selector will be off. Those selector will be on.
No, I mean the word line for the same bit line.
For the same bit line, what do you mean? You mean here?
Yeah. So for that case, won't there be some current flowing through the cell?
Yes. So that's why we need this selector. So if you think about here, then this voltage decaying, that means this VR will be smaller than this VR. Then you will have some current contribute into this. Then that's not good, okay? That's not good. So because you only want to read this cell, the readout current only depend on that selected cell, okay? You don't want the other rows to interfere with this. So then that's why we need the selector. We will discuss that. So this is exactly the problem, okay, we are going to discuss here. So this is a cell you want to read, okay, you only want the readout current proportional to this conductance of this cell. But this is cross-point array, okay, essentially it's a resistor network. The current can flow anywhere, right, can flow anywhere. So for those unselected cells, this will be the so-called sneak path through here. So this is exactly the problem. And then we need to get rid of this sneak path by this selector. If it's pure resistor, okay, then the current will flow anywhere. So what makes this selector? Essentially, you need some rectifier in the I-V characteristic. So essentially, you want a switch, right? Only this cell, when you select, you have the switch turned on. For all other cells, you want to have a off. So how do you do that? Ideally, if you, let's say the R, this is the R resistor, right? You have two high or low resistance state. So we have two straight lines. This is a very simplified physical picture. Very simplified. Okay, let's have two straight lines. That is I-V, right? So this is I-V. So straight line is the resistor. And you have two resistance, high and low. So it's like this. And then if you have the selector S, ideally it should be some rectifier like this. Okay. So above the threshold voltage, you turn on, and below the threshold voltage, the current is 0, ideally. So if you combine the 1S, 1R, then you will have this kind of combined I-V. They are in series, 1S, 1R. So that means below here, below this threshold, you will not turn on the selector. Only when the selector is larger than the threshold, then you will have the margin of the on and off, depending on the resistor's on and off state, high and low. So that means for the other cells, because as we just discussed, for the other cells, you don't fully bias. Only the select cell, you will have V, right? For the other cells, you have V over 2. So if you want to design this, you want that V over 2 to be somewhere where? So this figure is not very good, clear, but and let's say if this is your V and you want your V over 2 to be somewhere below the threshold, right? If this is a V and this is your V over 2, so of course this is not very proportional, but if you think V over 2 is somewhere here below the threshold, then you don't have current, so you cut off that snake path.
So if we can engineer this, we can use the V/2 programming method, right?
Yeah.
And
If you can engineer your threshold voltage and then, yeah. But this is ideal selector, there's nothing like this, and after this you fully turn on and below that you fully turn off. So you can think of a diode, right? Diode exponentially, but it's not, still you have leakage at below the threshold. So this is the selector, and let's look at some of the real selector. So as I just mentioned, what make a rectifier of the current? You can think of immediately. You can think of a diode, right? Diode, the I-V is exponential, so that means at small voltage, the current will exponentially decrease. Okay. So for the R1 devices, actually you need a bidirectional kind of diode because you need to use bipolar switching, right? So you need to normal diode. If you talk about PN junction, it's just one-dimensional. You only can turn on the diode by positive voltage to the P side, right? So, but we need to have some bidirectional diode through some engineering. So let's assume if you have this kind of bidirectional diode, this is the I-V in log scale. So this is exponential, this is in log scale. And then this is a typical resistor R1 device in log scale of the current. So if you combine that, you will see this kind of characteristic. So the dashed line is the original resistor I-V, and then the blue line is the selector I-V. And then if you combine that, then you'll get this kind of red curve, which is 1S1R I-V. So how would this help if you look at this? So previously you can see that, let's see. Previously, if you don't do this selector, if your red voltage, your voltage is here, and half voltage, let's say your voltage is roughly like 1.5, half is roughly here, 0.7. So this one, if you do nothing, this dash line, you only, because it's in the resistor, right? So you only decrease current by 2 times if it's a pure linear resistor, right? You only have current reduction by 2 times. Right, from here to here. This is on a log scale, so it's not linear. This is actually bended in the log scale. If you have linear relation in the log scale, actually is bended. So you only reduce by 2x. But with this 1S, 1R, you see here, this is a zoom in plot. Zoom in of this part. So you can see this red voltage, and then this is half right. So your current reduced by n times. So we define this N as a nonlinear nonlinearity ratio is defined as current at right voltage divided by the current at half right voltage. This is specific to the V/2 scheme. Okay, so you can see here in this experimental data, it's reduced from this like more than 10 micron to close to 1 micron. So it's reduced more than 10 times. But if it's a linear resistor, you just reduce the current by 2 times by changing from V to half V, right? But with this selector, because of the nonlinearity, you reduce the current by more than 10 times, or maybe 20 times in this case. So you can reduce that sneak path current. So that's why you need this selector. And ideally, so here we have some ideal selector, which I don't know the exact mechanism. This company didn't disclose the material. But this is purely, let's say, very ideal, because this is the log scale, and this is like your threshold voltage. And below threshold voltage, the current is almost 0 in the picoline range. And after that, it's like hundreds of micron. So in the on-off ratio, this guy is like 7, 8 orders. So if you combine 1S, 1R, you will get this kind of behavior. And this is really ideal, because here, this is right voltage. At right voltage, you will get like this tens of micron. And then you have this V/2 here. Then you reduce the current to like picoline range. So this is really good in terms of the nonlinearity, the definition, the current difference between those 2 points. So this is another example. And here, this is a quick summary. I will not read this. So there are 2 kinds of selector. One is based on this exponential I-V, which is the first example. So the red curve is the selector, the I-V is exponential. The second one is called threshold I-V, so it's very abrupt after this turn on point. So it's very abrupt. So this is the second type. So of course the threshold I-V is better, but depends on what is the on-off ratio of this. So I have some text here. I will not read that. So if you look at the category of the selector, there are many available devices, but not, and let's say a few of them are practical. Okay. So first is diode type, like PN junction, but the PN junction is not good, because first is unidirectional. It's only good for phase change memory. But the key challenge is that PN junction needs to be in the front-end process. You have to do the PN junction in the silicon substrate. You cannot build this PN junction with the memory on the metal. We just talk about metal 3, metal 4. You cannot do it. So then this is not very good. So then volatile switch, that's threshold switch on insulated metal transition material. And then nonlinear device, this is like the exponential I-V. So IBM has some devices called MIEC. I don't know exact composition. And the other kind of selector is based on this internal barrier selector, fundamental selector, and so on. So there are many papers on this topic, but not many of them are useful. So that's why today this is really challenging. That's why only Intel and Micron can do this, not any other companies can do this, because this selector design is really very tough. So for example, we can see some papers from literature. And this one is through the peroxide selector. So the idea is that we have some band diagram engineering for the 3-layer oxide. This is similar as what I discussed in the flash. You can have the H-shaped barrier, H-shape. So that at no voltage, then the current, the electron will see a very thick barrier, and at high voltage, the electrons will only see a very thin barrier here. So then you can use this to have exponential I-V in both directions. So then in this on-off ratio, right? So from V and half V. And the second one, this one is called OTS. So it's a Ovonic threshold switch. And this is a little bit, let's say, strange, because this material is the same as the phase change memory, used like charcoal-genet material. But the detailed composition may be a little bit different. So this material is like phase change memory, but it does not go through the phase change. That does not go through the, let's say, the crystalline to amorphous transition. But the material is very similar as the phase change. So the mechanism is not well understood. Some people say this is because of charge trapping and detrapping process. So this is still not very clear. But, okay, Intel and Micron is using this one. Okay, this is what I can tell. So of course they don't disclose the exact composition and the exact operation mechanism, but this one is what Intel and Micron is using, and this one is the only one that is used in the product. And there are some other research going on for this like niobium oxide. Even in my research group, I have done this. So this is based on this material, and this material can show this kind of abrupt switching and beyond some threshold voltage. However, the challenge here is the on-off ratio is not very large. It's only like 100. So the on-off ratio, let's say this is nonlinearity, how large you need depends on how large memory array you are building. So the larger array size, of course, you want higher nonlinearity. So this is another research paper. I will not go into the details, which I don't think this is promising. So basically, this is a CB-RAN device, but the retention is so poor. So after you form the filament, then the filament will immediately disappear. So then it's like you turn on and off very quickly. But this one has a lot of variations, as you can see. This threshold voltage is not very stable. Very hard to design the real circuit. Okay, so I put together a survey of those selectors in terms of the characteristics. I will not go into the details, and this is more for the research. I don't require you to understand all of them in this class. So what is important in this lecture is the crossbar array operation, and the V over 2, V over 3 schemes, because you will see that in your homework. Okay, so this is again the category of the selector. We have talked about that, and I list the pros and cons for each of this category. And this threshold switch is the most mature, and this OTS is used by the industry. Okay, so that's